In this video, we'll discuss a variant of the contrastive divergence algorithm known as persistent contrastive divergence. So we've seen that the contrastive divergence is actually a fairly simple algorithm for training restricted Boltzmann machine. It requires that for each training example, we sample what we call a negative sample, x tilde, which is generated by performing just a few steps of Gibbs sampling, which is initialized at the training observation xt. And then the update of the parameters has a very simple form, which involves computations both at the training example and at the negative sample x tilde. I've also discussed at the end of the previous video that this algorithm, CDK, where k is the number of Gibbs step, was actually a very good algorithm for training a restricted Boltzmann machine to extract some useful features, which is represented by the vector h of x. So h of x is the vector of hidden unit probabilities, and what we could do is train a restricted Boltzmann machine on some unlabeled data, and then we could change our training set or our data set in general, all of our data, so that instead of representing it by the x vector, we could represent it as the h of x vector, and then use that representation to train say a classifier. Say if we're classifying images of digits, we could feed that to that new representation to a linear classifier or another neural network. We'll discuss also we can use that to initialize a neural network, but the CD algorithm with k equals 1 actually works really well for extracting a good set of features. However, when it comes to evaluating on, say, a validation set or a test set, what's the value of the average negative log probability or log likelihood? It turns out that it's not doing that well. It tends to perform not so great. The reason for that is, so let's look back at our intuition for what CD does. So imagine I have an energy function which looks something like this, where this would be linear organization of all values for the x vector. And imagine I have a training example here. So that would be one training example. So what CD does to get an x tilde is that it starts Gibbs sampling there, and what Gibbs sampling does is that it essentially jumps like this, and say I do k steps, then maybe Gibbs sampling would essentially fall, say, on that point here. It doesn't go much beyond that point because the energy is much higher here, so the probability of sampling in these points here is actually quite small. Now, because we do only k steps of Gibbs sampling, actually the probability of going well over here or here is actually quite small because I'm doing just a very few steps of Gibbs sampling, and each step really goes doesn't go very far away from its previous point. Now imagine that my energy function is such that there's then a cliff, and then there are values for x here which actually do have very small energy. But because I'm using few steps of Gibbs sampling, it's actually impossible for the Gibbs sampling chain to actually go like this and eventually reach these points. So this going from here to here might require a lot of steps of Gibbs sampling for such a trajectory to be likely. And because of this, it means that there will be regions with CD1 or CD5 which will not get their energies raised. And because these are regions of the input space which doesn't have training data, then it means that when we renormalize the exponentiated negative energies, the relative probability of this is going to be higher. It's going to be lower, sorry, because we've assigned low probability elsewhere, and because everything needs to sum to 1, then it means that if I'm assigning probability here, then I need to assign less probability here. So we'll see a very simple modification of the contrastive divergence algorithm, which was essentially partly solve this problem and yield a much better estimator of the and a much better model of the probability distribution that generated our training set. So the idea is actually quite simple. because we're performing few steps of Gibbs sampling in between updates, it means that we can never wander too far away from our training example. However, in the previous iteration, so before our previous update, we actually had performed some Gibbs sample, and it's actually kind of a shame that we can't reuse this sampling to generate our next sample for our next update. And the idea of persistent CD is actually quite simple. Instead of initializing our Gibbs chain to the current training example, we will actually use the xtil that we sampled at the previous iteration, so before our update based on the previous training example. And that's it. The rest of the algorithm stays exactly the same. So this means that if I've performed, say, 10 parameter updates, and I'm performing just one step of Gibbs sampling for every update, xtil is going to be fairly close to the result of performing 10 steps of Gibbs sampling instead of just a single step. It's not exactly this, because in between, so during the Gibbs chain, the parameters of the RBM will have changed because I'm updating the RBM as I'm doing this. But still, it will allow for xtil to wander further away, much more far away from the training examples than if I keep reinitializing the Gibbs chain to the training example. And in practice, what we see is that indeed, by performing this very small change, we get a much better estimator of the distribution, and we get much better performance in terms of negative log likelihood of the validation set or the test set, so of new examples. Also, I should mention that in practice, often, instead of performing this in the stochastic way, we'll actually use a mini batch variant of this algorithm. And also, instead of maintaining just a single Gibbs chain that keeps being updated, so instead of having just one sequence of xtil, we actually often maintain a mini batch of xtils. And so, in other words, there will be many Gibbs chains that will be Gibbs chains that will be maintained in parallel during training. So, if you want to know more, you can look at the paper by Tillerman at ICML in 2008. And so that concludes our explanation for persistent CD.